yet. Let's wait to talk about the test until you get them back, and then I can answer questions if you have questions. All right, so we've been talking about the first law of thermodynamics. The first law of thermodynamics is basically conservation of energy. And the first law says the change in energy in your system is equal to Q, that's the heat that comes into your system, the energy that comes into your system through heat, minus W, and W is the energy that leaves your system through work. And notice that E is equal to the kinetic energy plus the potential energy plus the internal energy. And all of these are properties. Okay, so E, kinetic energy, potential energy, and U are all properties. That's something that describes the gas, the system, at a single instant. Q and W are not properties. They have no meaning at a single instant. They only represent processes. Okay, so now we're going to go on to a new form of the first law of thermodynamics. You use it in the same way, but now we'll go on to the differential form of the first law of thermodynamics. And that is dE dt is equal to Q dot minus W dot. And you're used to, well, maybe you haven't taken dynamics yet, and maybe you haven't seen the dot notation too much. You probably did in Physics 1 a little bit, but normally when you see a variable with a dot over the top, it just means the same thing as the time derivative. But here we're using, so it's a little odd to see like the ddt notation in the same equation that you see the dot notation, because they mean the same thing. Here we're doing that because Q and W are different things than E. And so you have to think about these differently. Remember, E is a property, okay? So there is such a thing as the time rate of change of that property. You know, it changes over time. Q and W aren't properties. You can't really think of it the same way. And so dE dt is the time rate of change of the energy. Okay, so the time rate of change of the properties that make up the energy. And it's equal to, you can break it up into the time rate of change of the kinetic energy plus the time rate of change of the potential energy plus the time rate of change of the internal energy. And each of these individual terms is a time rate of change of a property. Q dot is the net rate at which energy flows into the system through heat. And the reason it's the net rate of change, the net rate energy flow into the system is because that reflects the sign convention of Q. And then W dot is the net rate at which energy, so what's this, flows into the system or leaves the system? Yeah, at which energy leaves the system through work. And we're going to break differential form of the first law problems up into two categories. The first is steady state. And steady state means, so if a system is in steady state, none of the properties change over time. Okay, so it's not getting hotter, it's not, the volume isn't changing, the pressure isn't changing, and all these other things that are properties. So remember, kinetic energy, potential energy, and internal energy are all properties. So those can't change either. Okay, so this means that properties don't change over time. And this is going to be an important idea as this class goes on a lot of times. Properties don't change over time. And that means that the EDT is equal to 0. And that means that all of those individual, DDT of the kinetic energy is equal to 0. DDT of the potential energy is equal to 0. And DUDT is equal to 0. All right, so if you have something in steady state, and like a lot of times, I mean, if you have if your system is like a motor or something, you're hoping that it's going to reach steady state at some point in its operation. You turn it on and some things happen. But if it doesn't eventually reach steady state, if it keeps getting hotter or whatever, eventually it's going to blow up, So a lot of times in commercial things, useful machines or whatever, that steady state idea is going to be useful. And then second type is basically non-steady state, but we call it transient processes. And that's where one or more properties are functions of time. And the first way that we're going to use this stuff is in terms of the three modes of heat transfer. So now we're going to talk about heat transfer. So these are useful in heat transfer, among other things. And the reason they're useful in heat transfer is that three modes of heat transfer, which are, anyone remember that from Physics 1? Probably half of you had it and half of you didn't quite get to it at the end. But there's, yeah, conduction, convection, and radiation. That's right. And that's the only way that, those are the only three ways that energy can move from one system, outside the system or vice versa, through heat. And all of those three modes, the equations that we're going to have to define that heat transfer is in terms of Q dot. This is sort of a pain, but, and I'll mention this again in a second, but the way that we're going to define the equations that we're going to use for heat transfer don't use our thermodynamic sign convention. So you're going to have to apply the sign convention on your own outside of these equations. Okay, so I'll get that in the notes in a second, but so energy can only be transferred through heat in three ways. Conduction, radiation, and convection. And by the way, what does it mean for energy to be transferred through heat? So energy can be transferred a few different ways. Two of them are work and heat. What's the distinction between those two ways? How do you define heat transfer? By the way, heat transfer is kind of badly worded. People say it because it's short, but yeah. Yeah, and I think the best way to anchor your thought about heat is it's a change in energy due to a difference in temperature. Okay, it only comes from difference in temperature. Okay, work, on the other hand, is a change in temperature due to the application of a force. Okay, so the distinction is whether you're doing it because of a temperature difference or because of a force application. Okay, and heat transfer, because you're not really transferring heat. Heat isn't a thing. A property is a thing. Heat is the motion of energy. So really it's energy transfer through heat, but that takes longer to say, so people don't really say it. Yeah. Oh yeah, so heat and work are both ways of transferring energy. Heat is the transfer of energy due to a temperature difference, and work is the transfer of energy due to the application of a force. Okay, so first, conduction. So conduction is energy transferred through a material particle to particle without the particles changing location. Okay, so the way it works is you have, some particles that are locked next to each other. They're not going to move relative to each other, but the first one starts to vibrate. Its temperature increases. That makes the second one next to it vibrate. That makes the one next to it vibrate. And in that way, energy is carried particle to particle without the particles. A particle never goes over here or over there, Like what? Well, no. So radiation is a different one of these three, but conduction is like if you heat up a frying pan, and then so the fire only touches the bottom of the pan, but if you touch the handle, it's hot and it's not because iron atoms are moving. It's not because a hot atom that touches the fire moves over to the handle. It's just that heat moves vibration to vibration until it gets to the handle.
So conduction, do we typically use it over a single material, or are we often talking about?
You can talk about, in this class, we'll only talk about one material. But yeah, you can talk about multiple materials. So remember, I said the next class that the mechanical engineers are going to take that's sort of along the lines of this class is heat transfer. I'm going to talk about heat transfer for like one day. You're going to take a whole class in heat transfer. So we're going to be doing the basic stuff here, and you'll be doing complicated differential equations related to it for a whole semester eventually, And you'll be dealing with, you'll be dealing with that kind of stuff in terms of the boundary conditions on your differential equation. So notice conduction can't happen through empty space. It can only happen through a material. So let's say it requires a medium. Can't happen through empty space. Yeah, a vacuum. Or outer space too, which is a vacuum. Yes, vacuum. And the formula for conduction is Q dot is equal to negative Greek letter kappa. Looks like a fancy short K. Times A times dt dx. Where kappa is a material property, so it depends on the material you're talking about. Called the thermal conductivity. That's a measure of how easy it is for energy to be conducted through that material, how quickly. A is the cross-sectional area. I'm going to say it as A is the cross-sectional area perpendicular to the direction of energy flow. I'll draw a picture that'll make that a little clearer. Cross-sectional area perpendicular to the direction of heat flow. T is the temperature of the material at a given point. Oh, is that it? Yeah. Okay. So that temperature is a function of location. You know, a material can have different temperatures all through it. And then X is the location along the line of heat flow. So if you're talking about the heat flow through like a metal tube, well, not a tube, but a solid pipe, you know. Then, and you want to know how much heat is going this way, say. X is parallel to that flow, and A is the cross-sectional area, like the window kind of that flow is going through. So this is the cross-sectional area, A. Any questions yet about that? All right, so here's how you can use this. So let's say that we have a pane of glass. That's supposed to look all 3D-like. And on the outside edge, so this is like the outside of the window, the temperature is 15 degrees Celsius. And on the inside of the window, the temperature is 20 degrees Celsius. And let's say the dimensions are 1 meter by 1 meter. Let's say the thickness of the glass is 2 centimeters, so 0.02 meters. For this glass, the coefficient of thermal conductivity is 1.05 watts over meters times Kelvin. And what we want to know is the rate of heat transfer through the glass. We're going to this isn't quite enough information yet. We're going to have to make some kind of assumption about how the temperature varies as you go through the thickness of the glass. So let's say that the temperature varies linearly. We want to know what's the Q dot that we would use if the room is our system. So the 20 degrees Celsius side is our system. Okay, well, we know we're going to use this equation that says Q dot is equal to kappa times A times the temperature dx. Did I leave off a negative? Did I give it? Yeah. And by the way, you know what that negative does? This is an important thing intuitively to understand. So we'll see it. We'll see how it works out when we do it. But what this says is the flow of energy through heat is always going to go, in conduction, is always going to go from the high temperature thing to the low temperature thing. That makes sense. Like that's going to end up being sort of a fundamental thing. The second law of thermodynamics is based on that. Heat is only going to flow from high temperature to low temperature. You know, you never open your freezer door and have your room warm up. You know, energy flows from the room into the low temperature thing. Yeah, well, I didn't really explain it. I just said that that's what the negative is doing there. It's requiring that conduction only goes from the higher temperature to the lower temperature. But if you want to understand it, you can think of like if dt dx. So if increasing x leads to a higher temperature, that's what dt dx positive means. Then the flow direction is in the direction of negative x. And if dt dx is negative, and as you increase x, you're going toward a lower temperature. That's negative. Double negative means the conduction is in the positive x direction. So it just takes care of the direction. Well, yeah, I guess from the furnace to the house, the furnace is hot and it flows to the house. Yeah. So let's look at a side view of the window. I'm going to look at sort of an exaggerated view. Bless you. And we'll say that the direction of increasing x is this way. This distance is 0.02 meters. And we need a way, so I'm going to call this my zero position. If the thickness of the glass is 2 centimeters, then this has to be positive 0.02. Now we need to come up with a function for the temperature. We need to come up with the temperature as a function of x so we can take its derivative. So T of x is equal to, specify that it's a linear function, so mx plus b. Let's say this is the 15 degrees Celsius side. This is the 20 degrees Celsius side. So the y-intercept, what's the y-intercept? 15, yep. Because when x is equal to 0, the function value is 15. And then the slope we'll do is rise over run. So what's the rise of the function over those 2 centimeters? 5. It goes up 5 degrees Celsius. What's the run? 0.02 times x plus 15. And so that function is 250. So 250x plus 15. So that's the temperature as a function of x. So dt dx is 250. We were given kappa. What's the A? So now you have to sort of think physically about the direction of the flow, that kind of thing. Yeah, it's going to be 1 meter squared. And I think when I described it, I actually said you can imagine that area, that cross-sectional area, as being the window that the heat flows through. This is literally a window with an area of 1 meter squared. But you're going to have to think about that. In each problem, you're going to have to think about what's the slice of this that's perpendicular to the flow of heat, and what's the area of that slice. Okay. So Q dot is equal to 1.05 times 1 squared negative times 250, and you get a value of negative 262.5 joules per second. So what does that negative mean? That means that the flow is in the negative x direction. The energy flows in the direction of negative x. You're going to have to use that sign in later when you take the heat transfer class. That sign is going to have to, you're going to have to do everything in terms of these signs because you're going to be doing everything in terms of differential equations. For the purposes of this class, you can just leave that sign off because you can just see what direction the energy is going to flow. So this is saying that energy is moving in the negative x direction. We know that already because it's always going to go from the high temperature to the low temperature. Okay. So that sign, you can use it or not use it. Later on, you're going to have to use it. Okay, so that's the Q dot here. But so you have to be careful at this point. That does not reflect the sign convention that we use in the first law of thermodynamics. And the reason it doesn't use our first law of thermodynamics sign convention is it doesn't have any idea what our system is. You know, we have to choose which side is our system, or if the window is our system, or whatever. So this doesn't use first law sign convention. Our system is the 20 °C side. So is energy going into our system through heat, or is energy leaving our system through heat? Question? Mm-hmm. Yeah. No, the reason we don't have to convert, you know, I could have converted both of those temperatures to Kelvin just to be on the safe side, and it would have worked out. But since we're only dealing with differences in temperature, you know. Well, it's because differences in temperature were what we used in the equation, and differences in Celsius are the same as differences in Kelvin. But maybe to be on the safe side, just switch anytime you have temperatures at a single location, like an actual temperature, switch it to Kelvin there, and then you know it'll work. But if we would have switched it, we would have had 293 Kelvin on one side and 288 Kelvin on the other side, and everything would have come out the same. Okay, so our system is the 20 °C side. Is energy leaving the system or coming into the system through heat? Leaving. So in this case, is Q dot positive or negative? Negative. Yep. It turns out in this case the sign was right, but that's random. Okay. You can't count on that. Okay, so every second you're losing 262.5 joules of energy through heat. Is that a lot, by the way? It's a lot more than like 100. Any idea how many, like say a kilocalorie, you know, like you eat 2,000 calories a day. Any idea how many joules that is? No, 8 million about. So a joule is a pretty small amount of energy. Yep. Is that a lot? I don't know. Over, oh, a watt is a joule per second. That's right. Yes. Yes.
So for Q dot, it's negative because we're saying 20 degrees room is our system.
Right.
So it's the opposite if it's the other side.
That's right. So if the outdoors was our system, that Q dot would have been positive 262.
You also mentioned saying the window as Q dot at that point zero or what?
I don't think I ever said the window is our system. I mean, I looking across the window, come up with a function just to see how the temperature was distributed across the window. But yeah, that wasn't saying that's our system. So if we said it was our system, then if we said it was our system, then we would have the same amount of energy entering through heat that we have leaving through heat. And Q dot would be 0. Yeah. Unless the window was heating up, you know, unless the temperature of the window was rising. Mhm. Is that what it is? That sounds like a lot to me. I don't really know. Um, yeah, you might want to put some kind of thermal cover on that window. That's funny though. That's not a very big temperature difference, but uh-huh. Yeah, yeah, and that's just glass, the coefficient of thermal conductivity that I used. And I think windows now are more complicated than that, right? They have some kind of glass with like a thermal layer in between or whatever, don't they? I think so. Okay, yeah. I'm not really a window expert, but I thought I'd heard that in a commercial. So yeah, like this would be like an old window, and yeah, that's why they don't do that anymore, I guess. Um, okay, so that's conduction. The next one is radiation. Um, and the idea of radiation is any object that isn't at absolute zero, uh, any object above 0 Kelvin or absolute zero emits electromagnetic waves. Um, Electromagnetic waves can travel through empty space. They can travel through a vacuum. Um, they don't require a medium to travel through. Um, and so radiation is the only mode of heat transfer that doesn't require a medium. Well, I haven't talked about convection yet, but you'll have to trust me. But radiation is the only way for heat to transfer through a vacuum. Um, and so, does vacuum have one C or two? Just two U's. One C, two U's. Okay, so let's just all take a moment to be grateful for radiation because all life on Earth is here because heat transferred from the sun through empty space to Earth. Okay. Uh, it. We'll talk about that. Um, yes, the things it does in a couple of ways, but we'll talk about that. Um, so the heat emitted. Again, that's sort of talking loosely. When you talk about heat transfer, it's really energy that's emitted through heat. Um, the heat emitted from a material follows the Stefan-Boltzmann law. And so Q dot sub E. So that's just emitted. Right now, we're not talking about any the net flow of heat, and that's going to be important. Is equal to Greek letter epsilon times Greek letter sigma times A times temperature to the fourth power. That Greek letter epsilon is called the emissivity. And that's related to the surface of the material. It's a pure number, so it doesn't have any units. Ranges from 0 to 1. Zero corresponds to a shiny white material. And 1 corresponds to a matte black material. And this emissivity is also determines how much heat through radiation is absorbed. And that's why if you wear a black shirt on a sunny day, it's noticeably hotter, you know. What you should wear is like a shiny metallic shirt, shiny white shirt, and then you stay cool. Sigma is the Stefan-Boltzmann constant. And it's equal to 5.67 times 10 to the minus 8 watts over meters squared Kelvin to the fourth. Notice in this one, we're not talking about a difference in temperature. So this temperature that you take to the fourth power needs to be in Kelvin. And then the last one is the surface area, the material. And notice again, I'm going to mention this with all three of these because it's important. The sign doesn't give you the sign for the first law. Again, this equation doesn't know anything about what we're isolating as our system. So you have to do that after the fact. Positive Q dot sub E just means that the object is emitting energy. And so if your system is if you are isolating the object that you're talking about emitting the energy, then that sign is always going to be backwards. Okay. but just you need to think about it separately after. Yes. This is the object that's radiating the heat. Yep. And notice that knowing how much energy is being radiated by an object is not really that helpful a thing for the first law of thermodynamics, because we don't, that Q in the first law of thermodynamics, or the Q dot, it isn't talking about how much energy is going out or coming in. It's talking about the net flow of heat. Okay, so if we know how much heat is flowing out of the object, but we don't know how much heat is being absorbed from other sources, there's really no way for us to use this. But there is sort of a common case where we do know the net flow of heat. So that's what we're going to focus on. So it doesn't help too much to know the heat emitted without also knowing the heat absorbed. But there is one case where we can calculate the net heat transfer. And that is when you have a smaller body. So for a smaller body, completely surrounded by a larger body, then Q dot, I'm going to say E because that gives us the sign convention of this equation. But this is the net heat emitted is equal to the emissivity times the Stefan-Boltzmann constant times the surface area A times the quantity temperature of the body, so T sub B to the fourth, minus the temperature of the surroundings. So don't think of those as big and small, that's backwards. Body and surroundings. Come up with your own subscript if you don't like it. Okay, so, and this, what do you think the emissivity is referring to? The emissivity of the surroundings or the smaller body? %50 chance. Smaller. And A is the surface area of the smaller body. So you can use this for stuff like if you have an object sitting outside, you can imagine the atmosphere as being a larger body surrounding the smaller body, and you can use this equation.
So the emissivity of the surrounding body is not important at all?
It's not important, right? For, like in that case where you're outside, where it would just be the air temperature. So 70 degrees or whatever. I don't have an example for that right now, but we will get to some examples. Oh yeah, let's make a point of that. So this is the net Q dot emitted. So look at the signs of the temperatures. So if you have a hot, smaller body surrounded by a cooler, the surroundings are cooler, then this is going to be bigger than this, and you're going to get a positive net flow of energy emitted by the smaller object. The smaller object is going to lose energy net. If you have a hotter surroundings, like a sauna, you're in a sauna surrounding a rock or whatever, this is bigger, you're going to get a negative value, and that means that the net heat is going into the rock. Okay. Or I guess he likes to be called, shoot, I can't remember his name. What's that guy's name? Dwayne Johnson. Yeah. Okay, that was stupid. And then the last mode of heat transfer is convection. And in this case, heat is carried to a new location by moving particles. Okay, so like I said, conduction is like a pan that you heat up on the bottom, and other parts of the pan get hot. Convection is like wind chill. Okay, so if it's 10 degrees outside and you stand outside in a t-shirt, okay, it's not very comfortable. But if it's still, the heat that comes out of your body stays in the air particles nearby and keeps you relatively warm. If you go out and it's 10 degrees, you're wearing a t-shirt and it's really windy, as soon as your body loses that heat, the wind takes it away from your body, and so you lose heat a lot faster. That's the idea of a convection oven. In a regular oven, if you're baking something in a regular oven, the cookie dough or whatever is at a relatively low temperature, and so the oven heats up the cookie dough, but the cookie dough also cools down the air around it a little bit. But if you have a convection oven, as soon as that air around the cookie cools down, the motion of the air gets it out of there and brings new hot air to the cookie, and that's why it cooks faster. Anybody here ever experienced the horror of having an ice bath after like sports practice? No, you guys are lucky. Okay, yeah. So ice baths are horrible, but so you dump, like, you get one of those rubber garbage cans and you dump a bunch of ice in, and then you fill it with water, and then you stick your leg in or whatever is injured. Or if you're really unlucky, you put on a pair of like thermal underwear and dunk your whole body in a tank. And so here's the experience, and here's how it relates to convection. So you get down in it, and you're just like, oh my God, this is the most horrible thing. You're like biting on a towel, just like, I can't survive. And then if you can make it through the first minute or whatever, then all of a sudden you start thinking like, okay, I'm getting used to this, or I'm getting numb or something. It's not so bad. And then the trainer comes in and stirs the bath, and all of a sudden it's as bad as it was again. Because what happens is you put your foot in, little by little, over the first minute, your leg heats up the water right around your leg, and it really isn't as bad, But convection, if you stir it, you get that warm water out of there. And so anyways, that's convection. Ice bath. And so the formula for heat transfer through convection, Q dot is equal to a constant H times an area A times the quantity temperature of the body minus temperature of the, let's call it F for fluid, that's the air, the water, or whatever. And convection can happen in so many different ways. I mean, if you were really going to try to come up with an expression for heat transfer by convection using like first principles of physics or something, it would have to take into account fluid dynamics and conduction as the convection's happening or whatever. Instead of trying to do that, we're just going to sort of use this catch-all constant H. It doesn't even try to represent like a physical thing. It's just it just comes from an experiment. So you have to do this experiment for your particular. So if you have a particular environment where you want to measure convection, you need to do an experiment to measure this constant H. There's no table or anything that says like here's H for air and here's H for speed of the fluid and how much turbulence there is and how much conduction there is in the fluid and how much. So don't even try. A is the surface area of the body that's exposed to the flow. And so notice that that's not the entire surface area of the body. So if you have a body that, say okay, imagine a carrot that's planted in the ground, and you want to measure the conduction on the top of the carrot or whatever as the wind blows by. You don't care about the part of the carrot that's underground. Most of it's underground. You only care about the top where the wind is going by. TB is the temperature of the body, and TF is the temperature of the fluid. Okay, let's do an example. Oh, I said I was going to do this for each one. So notice the sign of Q dot doesn't give a sign of Q dot that you're going to use in the first law. So that's true of all of those. All right, so let's say, so we're actually going to do a first law problem with this one. So let's say we have this gearbox. And don't screw up this drawing either. Okay, so there's one gear. I just didn't draw the teeth. And then there's another gear that articulates with it down here. And the cross-sectional area of this box is 1 meter squared. And there's work done over here. That's the input. And after it comes out of this gearbox, it turns this gear to do work. That's work to output. That's what you use the gearbox for. And let's say that this box is cooled through convection. And our experiment told us that H is equal to 0.171 kilowatts over meter squared times Kelvin. The temperature of the box is 300 K. The temperature of the air surrounding it is 293 K. And we want to figure out two things. The first one is the convection problem. So what's the rate of energy transfer by heat? What's the rate of heat transfer? And then second, let's use that in a problem using the differential form of the first law of thermodynamics. If the box is in steady state, what's the work that's delivered by the box? So what's the W2? And what I didn't write up here is W1. So we need to know how much work is input to the box. So work 1 dot, just the absolute value of that is 60 kilowatts. Okay, so first of all, the box is a little warmer than the air, so the heat transfer through convection is going to be away from the box. The formula says Q dot is equal to, I'm going to just put everything in SI units, so we have 0.171 times 10 to the 3, whatever the crazy units are, but that just gets rid of the kilowatts. So now we're in watts per meter squared Kelvin. The area that's exposed to the air was given, that's 1. Hovering in space. Well, or just imagine that this area that I gave you here only gives you the area that's exposed to the air. Remember, that's important. And then the temperature of the body is 300. The temperature of the air is 293. And so the rate of heat transfer is negative, no it's not, is 1.197 times 10 to the third watts. Okay, and that's a wave, yes? Yeah. That's the outer surface area of the box, only taking into account the part that's exposed to the air. So probably, most likely, the way I'm imagining it is, that's a huge gearbox. But, sitting on the ground like this, that's the surface area of the 5 faces that are on the ground. Okay, so that's the rate of heat transfer. Now we're going to use the differential form of the first law of thermodynamics. And that says the EDT is equal to Q dot minus W dot. Remember that we haven't thought about the sign of this energy transfer, so we're going to have to do that. The good news is this box that's our system is in steady state, and so all of the time rate of change of properties goes away. So you can always do that for steady state. What? Yeah, right. And most often there won't be kinetic or potential. They'll just be du dt. But if it's steady state, then you get rid of it. What? Oh, okay. Okay, feel free. So now we have to think about the sign of Q dot. So our first law sign convention says Q and Q dot are positive if energy is going to the system. Is energy going to the box or away from the box? Away. So this becomes, so 0 is equal to negative 1.197 times 10 to the 3 minus W dot. And so, oh, and there's one more thing I have to do. We added work up here, right? We added 60 times 10 to the third watts. If you add work to the system, is that positive or negative? Negative. So we can think of this as 0 is equal to negative 1.197 times 10 to the third minus 1 plus work 2. So 0 is equal to negative 1.197 times 10 to the third minus negative 60 times 10 to the third minus W2. And so W2 is 60 times 10 to the third minus 1.197, which is 58.803. Times 10 to the third watts. Okay, so knowing that the gearbox is in steady state and knowing how much energy is being carried away by the air lets us calculate how much of the work that's put into the top gear comes out in the bottom gear. Any questions about that? Okay, have a good weekend.